To understand its rarity, we have to understand its band structure. Three important elements. 1. The valence band, where electrons live. They cannot move because there are as many electrons as quantum states available. They can ascend to another band if they have enough energy, but they can never be in 2. The gap, a forbidden area for the electrons. You will never find one there, but if an electron has enough energy, it can reach 3. The conduction band, where electrons have empty quantum states, so they can move freely through the material in the form of electric current. Important, among other things, the size of the gap determines the conductivity of the material. A large gap, you have an insulator. A small or null gap, you have a conductor. As you may have guessed, a topological insulator is an insulator, has a big gap, but it's a very peculiar insulator because its electrons are under a strong spin-orbit interaction, a relativistic phenomena. This interaction makes some states of the conduction band exchange position with some of the valence band. So what? Well, inside the material nothing happens, but on the surface it is another story. We have said that the states do not exist in the gap, but on the surface of insulators this rule is often broken. These states are offspring or descendants of interior states, that is to say, they belong to the family of valence or conduction. And here is the problem with topological insulators. Because some members of the family have been exchanged, the surface states inextricably join those families, that is the valence and conduction bands. Furthermore, these states always come in conjoined pairs, each state with its opposite spin, Kramer's theory. Ultimately, these states permit the emergence of pairs of electrical current along the surface of the material, where they flow with reverse direction and spin. This is called helicity.